Okay, this is the first lecture after our midterm examination. So let's go to the review of our previous midterm examination. So we have first 4 problems which are quite easy. So let me just directly go to problem number 5. It was the problem about deriving the input and output relation of a CMOS inverter when both transistors and MOSFET and PMOSFET are in their saturation mode. So we must have the sum of drain current, which should be 0 in this case. Then we can make a lengthy expression. So due to the output resistance, we have the terms like 1 plus lambda of our output variable ID, n is proportional to this quantity, and also IDP is also proportional to 1 plus lambda p, and V out minus VDD. So this is negative quantity and this is also negative quantity. So when we sum them all or make a product, then they contribute positively. So here we have the terms proportional to C out, and also here we have the terms proportional to C out. So not C out, B out. So B out can be expressed as in terms of V in. So that was problem number 5. And problem number 6 was about a similar problem, but let's consider CMOS inverter, and we don't care about this term and that term that are related with output resistance. In this case, we try to find out the inversion threshold. So Vin, in this case, our input voltage and output voltage equal to V inversion threshold. So it was already covered in our lecture, and when we define the ratio between our PMOSFET strength and MMOSFET strength, then we can arrive this form, so you can easily understand the solution. And when you go to, so if you have any question, then please let me know. And let's go to problem number 8. So problem number 8 is, what is N for the threshold, sub-threshold slope of 100 millivolt per decade? So here N means that the expression shown here is given by ID equal to certain constant. This is not source current, but this is just a constant, and exponential of VGS over N times VT. So this is summer voltage, and here of course we have some terms related with VDS, but that is really exponential minus VDS over VT. So when we have VDS, which is much higher than summer voltage, so please note that this is just about 25 millivolt. So if we apply 0.1 volt or higher voltage, then this term, exponential term, quickly goes to 0. So simply speaking, our sub-threshold current can be well represented by this form. So when we have a sufficiently high drain voltage, then now we can concentrate on this expression. The next thing is quite simple. subthreshold slope simply means that how much additional voltage is required to increase our drain current by factor of 10. So let's say that we have a certain voltage VD naught whose value is given by this way VGS, a certain voltage, and N times VT. And by definition of our subthreshold voltage, then we will have 10 times higher voltage, 10 times higher current when we have the additional gate voltage like something. If we add something, then we will have 10 times higher current. But how large is it? So here 100 millivolt per decade means that we need additional 100 millivolt to increase the current by factor of 10. So simply speaking, here we must have 100 millivolt. So now we can eliminate these common factors. So common factors can be eliminated. For example, this guy, this guy, this guy, and this guy. And also we have the same exponential factors. The remaining thing is 10 is given by exponential of our 100 millivolt additional voltage divided by this voltage scale. So after that we can take the natural logarithm both sides, then we have 10 and it will be NVT 100 millivolt. That's the reason why our N value can be simply given by VT log 10 and 100 millivolt. So typically, when we evaluate this quantity, we realize that at 300 Kelvin, this value is really corresponding to 60 millivolt. So the answer will be about 5/3, but you can of course calculate quite exact value. Okay, so anyway, that is the way to calculate our N value. Of course, the ideal case N should be quite close to 1. So if we have the N value which is really close to 1, then we achieve the case of 60 millivolt per decade case. This is quite good. And let's say that if we have 100 millivolt per decade, so which is a much degraded one, then let me just make a comparison. If we wanted to have at least I1 and I0 larger than 10 to the 5, at least if we have this kind of subthreshold slope, then we need at least 3 or 0.3 volt between our off voltage and on voltage. And if we have 100 millivolt per decade subthreshold slope, which is a degraded one, then in order to achieve a certain value, in this case 10 to the 5, then we need 0.5 volt. So are you with me? In order to get the same amount of on and off ratio, so if you have worse or degraded subthreshold slope, then your voltage spacing should be high. So in this case, you cannot reduce your VDD any further. And if you have a better subthreshold slope, then maybe you can try to reduce your VDD value. That is critically related with your power consumption. We will see it in today's lecture. And now let's go to problem number 9. So here, unfortunately, it was a difficult problem to most of you. So I just make a verbatim from our lecture material. So our problem was like this. Here we have a certain CMOS inverter, and here we have another CMOS inverter, and they have different ratio between their N MOSFET and P MOSFET. So P MOSFET to N MOSFET. So in this case, this is a 2 to 1, the typical one, and 2 to 1 is now changed to 10 to 1. Then what happens to three quantities like high logic level and low logic level and static power consumption? So the answer is quite easy. High logic level is always VDD, and low logic level is always just 0 volt ground. And in the case of CMOS inverter, if we neglect leakage current, then static power consumption is quite close to 0. So in ideal case, without the leakage current, so the answer is these quantities are not that much affected by this kind of change in their P to N ratio. So, but unfortunately, our students are a little bit confused by this level, high level, low level. Instead of that, they just try to understand like this. So they try to measure the noise margin for both of them, so low input and high input, but this is not my question. My question was this level, and this level is affected by this ratio or not. So please note that it has the ratio-less properties in the case of CMOS inverters. Okay. And another problem is now problem number 10. Okay, so problem number 10 is we assume that our input voltage is 0. So now we have inverter and input voltage is 0. So now we have VDD or logical 1 as an output. In this case, inside this inverter we have two transistors. One is P MOSFET and one is N MOSFET. Also this N MOSFET is completely turned off because the gate voltage equal to 0. So only this P MOSFET is turned on. So when you consider the output resistance seen from this output node, then since this N MOSFET is completely turned off, it will contribute to extremely high resistance. But in this case of P MOSFET, it will give us a moderate value of resistance. So only this one will be seen from our output node. So first of all, we have to understand this is nothing but the drain resistance of our P MOSFET when it is biased to gate voltage equal to 0 volt. Okay, so however, all of our students fail to correctly calculate the resistance of a P MOSFET in its linear mode, unfortunately. So please try to understand what is the resistance in the linear mode. Okay, so then now let's go to problem 11. Oh, sorry about that. This is not problem 11. So this is for problem 14. Okay, sorry about that. This is a typo. we have to consider this one. So every student successfully calculated this minimum effort delay, so it's good. However, students just show such kind of things. So our effort delay can be obtained by a sum of uh, these two factors, g times h. So sometimes the first stage have terms like this, and second one has 5, 3, and sorry about that. And third stage, and the last stage once again have this one. So our students said that okay, we must have the same values. Okay, you are right. They should be the same. However, can you calculate x, y, and z only from this relation? So please think about it. So you must have something additional. So that was my comment. So when our today's lecture is over, then let's make some sessions to review your answer sheet. So I will distribute it to you. So please, so give me your feedback on your score. Then I will finalize your score. So I just collected some problems which seems to be important to be reviewed. So anyway, so do you have any question? So you will have some time to review your score. The session is over. Okay. Okay, then let's go to our main discussion about power. So in order to have some time slot for reviewing your answer sheet, so I will make a relatively short discussion on our power. Okay, so this is just the introductory one. So now we are talking about the definition of our terminology. Okay? Here we introduce instantaneous power consumption at a given time. So at any time instance t, so its power consumption is given by this way, I times V. So this is the power consumption, and it's like this. So say, so simple analogy is like this. Here we have a certain hill. Yes, this is ground, and here we have a hill, and let's say that there is a ball. Maybe you know this one. So what happens if we just kick it slowly? Then everybody understand. In the case of the frictionless case, what will happen? Here we have a ball, and you just slightly, smoothly kick it. So initial velocity is quite low, close to 0. So now you understand, if you have studied the general physics, then you can understand when it comes here, then of course you have the reduction of your potential energy. However, the loss of your potential energy is converted to what? Converted to the velocity whose magnitude is much larger than 0. So you understand the conversion from kinetic from the potential energy to the kinetic energy. So when I ask you the question whether the total energy is reduced or not for this ball, then you can say that although it is converted from potential to kinetic energy, the total energy seems to be preserved. So are you with me? However, this is really ideal case like frictionless. Now, instead of this roller coaster like situation, but say that this is the real ground. So now you understand there are so many obstacles here. So let's say that what happens if you just gently kick it, then let's say that there is certain motion. However, it's not that fast, and eventually it will just stop here. So it's in realistic case, its velocity would be also quite close to zero. Although we have had reduction of potential energy. What happens where this potential energy goes away? It is no longer belonging to this ball. So friction between this ball system and this ground and obstacles on the ground, they consume the energy. So energy is spent in that way. So let me just come back to our instantaneous power consumption once again. Why do we have this kind of thing? Still, here we have voltage. So here we have voltage. This is a relatively higher voltage, and here we have a relatively lower voltage. And if we have electrons here and electrons there, then they can have different potential energy due to the voltage. So this reduction of voltage is not converted into the increase of our electrons' kinetic energy. More or less in our electronic circuit, they have more or less average velocity, and they have also average velocity. So although, for example, if our electron moves from high voltage to low voltage case, it does not gain or lose the average velocity. So there is no increase in the kinetic energy. Then what happens? What happens to this loss of kinetic potential energy? This loss of potential energy is just typically in our case goes to the heat inside our system. Okay, so are you with me? So that's the reason why we simply say that in many cases we just draw a resistor and say that let's for example 0 volt, and let's say that this is V, then we will have a certain current. And if we have higher current means that we have more and more electrons are moving. And when more electrons are moving, then yes, each of them just to lose the energy corresponding to Q times V. For one electron lose amount of Q times V. For example, if one, let's say that one point and another point, between them we have 1 volt difference, and we just move our electron from here to there, then what is the energy difference between these 2 points? So when we just consider magnitude, then we can say that there occurs the change of energy corresponding to 1 electron volt. Also, yes. So 1 electron volt, which is given by this E is corresponding to 1 times 10 to the minus 19. So this electron volt, 1 electron volt is 1.6 times 10 to the minus 19 joule. Okay, So let's say that our electron, one electron is moving. Then this is related with change of 1.6 times 10 to the minus 19 joule. Instead of that, now we have two electrons are moving the same way. Then how much the energy difference is related? You can just multiply number 2 because there are two electrons are related. So simply speaking, if this uh, current is higher and higher, it means that more electrons are moving in a given time scale. So amount of energy dissipation to what? To the heat is enlarged. So that's the reason why we have I here, also V here. So here V is corresponding to the energy loss due to one single electron, and this I represent how many electrons are involved in this energy losing or energy dissipating procedure. So are you with me? So this is quite a simple concept we can have. So this is really instantaneous value. So please wait for a while. So we must, our pencil is once again stuck. Okay. So now we have terms like power. So unit of power is simply given by, although we say that this is watt, but this is energy dissipation per unit time scale. So when we make a time integration of power, so simply speaking, time integration of power, which is given by energy divided by time, then we can easily convert how much energy is lost during this time period t. Okay. So if you have any question, then please let me know. Then this is quite a general expression. Yes, this one is a quite general expression, but here we have one assumption about the meaning of this large T. So although this is a quite general one between time period 0 time equal to 0 and time equal to t, however, instead of that, in this expression we make a certain assumption. Okay, now t is interpreted as a period. So let's say that period. If we have this periodic signal, then a period is corresponding to a time interval where our electrical signal is recovered in its original position. So when we have time equal to t and t plus capital T, then their values are the same. And when we add once again t plus 2 times capital T, then we will have the same value. So this is the period. In this case, we can make an average. So here you can see this is just the energy dissipation during a period, and this is divided by once again the period. So it will give us the average energy dissipation, power dissipation in a period. So we will have the average value. Okay. Now think about this inverter system. Here we have an inverter, of course, and now we have this capacitor. So this is a load capacitor, and here we have this one. And now we wanted to charge this load capacitor. Then how can we charge it? In order to charge this one, then it means that it should be logical 0, logical 1. So input should be logical 0. So starting from the original input logical 1, then of course that will be 0. The empty capacitor. After that, when we abruptly increase or abruptly change our input voltage 0 to 1, so when input is changed from 1 to 0, then our output will respond in this way. Now it is increasing, and now since this is our capacitor voltage, output voltage, so this is the charge phase. Everybody can understand this one quite easily. Then now I wanted to discuss about how much energy is spent to store or charge our load capacitor. So now think about this one. Here we have I times V. Here I is given by capacitor current and V is capacitor voltage. So you know this is power. And now in the case of our capacitor, can you recognize the form of this I? When this is a capacitor, then this is nothing but C times V out of VT. No. So when you just insert it, then C times V times dV over dt, and its time derivative is required. So this is quite a simple one. So we can pull out the constant C, and we can easily understand this is nothing but the time derivative of half times square V. This is corresponding to this. So simply speaking, now our result will be C times half square V evaluated at one position and one time instance and another time instance. So what is the ultimate value of our output voltage in this case? In this case, we wanted to charge it, so eventually that will become VDD. And what is the initial value? Initially, we considered completely empty discharged capacitor, so it will be 0. So when we combine them all, then we can find that this is half C times V squared. This is one we can easily understand. So, but please note that although this is a general expression for power, but in this case we have used the terms for capacitor, and also this is the V out is the term for capacitor. So the calculated energy in this case is not for the entire system but only for this capacitor. Yes, after charging this capacitor, we will store this amount of energy into this capacitor. Actually, who charge this capacitor? So ground or your beam? No, they do not charge this CL. The charging is done by your VDD. Your VDD supply the current, and the energy is stored in this CL. But we must understand in between the VDD and CL we have a P MOSFET. Yes, we have a P MOSFET, and this is a resistive one, so it spends its own power. Okay, so let me just make another, although crude, but analogy on this situation. So let's say that there is a jar and we have certain lake. So this lake is corresponding to what? So our VDD. And here we have a little bit small jar. This is corresponding to our CL. We wanted to just fill this jar with water. So now we must have some connection. Then water flows from here to there, and this jar is completely filled. However, let's just say that this connection itself has some leak property. Yes, it has some holes. Then what will happen when water is coming to here and finally entering into this jar? Then there will be some losses. So now I'm saying that after this filling period is over, then we will have a certain amount of water collected in this jar. However, we can also think about how much water is just wasted to move from one position to the another position. That is, how can you calculate this one? One way is to calculate it this way, just to collect them all. However, another way is if we can just see here how much water is spent in this position, and also measure how much water is collected in this case, then we can think about the loss. So for example, I gave 100 and you get just 30. Then what happens? 70 is lost. I gave you 100 and you get just 10. What happens? Yes, in this case 90 is gone through this case. So now we wanted to calculate the power spent by this lake or spent by our VDD. In terms of our VDD, then how can you calculate the entire energy spent by our power supply VDD? Still, we must calculate I times V. However, previously we just consider out voltage because we were interested with the energy stored in this point. However, right now we are considering the total amount of energy spent by our VDD node. So the voltage is no longer V out, but we must consider now VDD. Okay, this is the voltage. And how about the current? Of course, we must consider the PMOS current. However, in this case, we make an assumption that our MOSFET is completely off, so we have no current at all. Then if we follow these graphs, then this convention, then we can say that IP, the PMOS current, is exactly same to what? Same to the capacitor current. So now we can say that this is just a capacitor current. Okay, so now then what happens? This is nothing but, yes, this is constant, and C times dV out and dt and dd. When we make a time integration, then C v dd can be pulled out, and now we have just dV out over dt time integration. What is it? This one gives us just v dd. That's the reason why this energy delivered from our power supply is not half of C VDD, C square VDD, but it is just C times square VDD. Okay? So now we are considering this one. Okay, from our power supply, I gave you C times V square, and you just receive half of it. This is a capacitor. Then what happens? Oh, in between we have P MOSFET, and this P MOSFET just dissipate the energy. Half of energy is wasted by this way. So you know this is the charging phase. After that, of course, the signal always up and down, and now let's consider this discharging phase. In this discharging phase, what happens? In this discharging phase, now our input voltage equal to 1, so our P MOSFET is completely turned off, and initially we have a fully charged one. Here we have V out equal to VDD. That is completely, that energy, stored energy, is completely dissipated by what? Dissipated by this N MOSFET. So when we consider this procedure, now we can understand this way. The procedure is quite simple. So in this charging phase, power supply gives C times VDD square, and half of it is spent by our P MOSFET, and only half of it is stored in our load capacitor. After that, this is charging phase, and we have a discharging phase. In discharging phase, initially the energy was stored in our load capacitor, and it is completely discharged or dissipated by our N MOSFET. Okay, so after that, what happens? We have no longer any charge, any energy stored in this CL, because our CL voltage changed in this way. Initially 0 and charged and completely discharged once again. So nothing is left in this final time period, and during that time, although power supply just to provide this amount of energy, but that is always gone by this P MOSFET and N MOSFET. So please note that in this kind of discussion, we have not thought about any kind of ratio and any kind of size of CL or size of IP, IN, whatever. So this is quite a general one. If you have 10 times wide one, or 10 times, only 2 times wide one, that doesn't matter. This one is just given by this general structure. Okay. So simply speaking, this switching is just a procedure to waste energy. If you turn it on and turn it off, or charge the capacitor and discharge the capacitor, what is left? So if you just measure the initial state and final state, then actually we have nothing, no charge inside it. The important one is during that time, we make some time derivative of our voltage, and it is regarded as information. So now we make some trade between our power consumption and information. So in order to process the valuable information, we are now consuming our power. That is the key point in this system. So always we must consume the energy. Yeah. This is really unavoidable. However, we want to minimize the amount of power consumed by our electronic system. So that's the reason why we are always quite hungry for low power system. In order to process the same amount of information, if we can do it with extremely low power, then maybe we can apply these electronic systems to more widely, and let's say that this is more beneficial to our humanity or our general good. Okay, so this page just to summarize the switching waveforms, so please have a look at it. Then now let's go to let's go to this page. I just skipped the waveform because I have already discussed this one. Yeah, so now let's say up to now we have spent the time for our energy consumption. Okay, when we go through one switching period, so charging and discharging of our load capacitor, we have learned that the energy consumption is simply given by C times VDD square. This is the energy consumption. But this is energy. Then how about the period-wise average power consumption? Not energy, but power. Since capital T is used for our period, then now we can make just a division by period, then that will give us some number. And 1 over t, what is it? 1 over t. This is a second unit, so now 1 over second is called as hertz. So now we have a certain frequency related quantity. With this frequency, the transistor or our system is turned on and turned off, turned on and turned off. So this is called as switching frequency. Then now you can see this important relation. So this relation is quite easy. However, this is so important. So now let's think about this one. Always we wanted to have a low power system. Then how can you realize this low power system? Then since we have 3 different terms, their effects are quite much obvious. So please try to imagine how can you do that in order to reduce the switching power consumption, then we must reduce the capacitance. Okay? And another one, that is, however, reducing this capacitance is not that easy. So, because this is related with also, speed. So maybe we have learned in our delay session, the size of our logic gates are much related with the speed or delay of our logic gate. So it is not a single problem. And another one is here we have VDD. If we have low VDD, then that can drastically reduce the power consumption. Also, you know that you will have square term. So, for example, if you reduce your VDD from 1 volt to 2.7 volt, and let's say that everything is the same, like capacitance is the same, and let's say that frequency, operational frequency is the same, then what will happen to your switching power? So, since we must calculate the, the square of it, it will give us 1 and it will give us just 0.45, 0.5. So by reducing our VDD about 30% reduction, then that will give us 50% reduction of our power consumption. Are you all with me? So this is the reason why we wanted to reduce the VDD in the case of a low power system. Okay. Of course, another one is reducing the operational frequency. So if, for example, if we never switch on and off the system, then the power consumption due to this switching will be completely zero. But this is not a reasonable way to reduce the power consumption. Anyhow, we must to operate our system. So within given frequency range, yes, more or less this one is given, then we must have certain technology which can provide us lower VDD and also can provide us a lower C value. Okay, so are you all with me? So if you use older technology, then typically it has higher VDD value, and typically your devices are consuming large area. If you have old technology, and if you adopt new technology, then this one relatively have lower VDD voltage and it has small area per unit circuit. Then what will happen? Please think about the benefit of this new technology. So if we just keep this operational frequency, then we can have some benefit from reduction of operational voltage and also reduction of capacitance for given functionality of logic gate. So that's the reason why we wanted to have the new technology, new generation of our technology. Okay, so I just briefly introduced this one, but if you are interested, please let me know. So therefore, I wanted to summarize this lecture. It is really important to understand this one. Yes, so reduction of VDD is really important. Okay, and this power switching is obtained from the case where we switch our logic gate every time. So every period we turn it on and turn it off, turn it on and turn it off. But now let's think about this case. A certain case, our waveform, although t is given by this way, then now let's say this is t period. Then every time period t, we will spend c times vdd square. But now let's think about this case. For another signal, blue one, I will write it down blue. Let's say that we have this kind of thing. So can you see clearly this blue one? So if we consider the first two time period, then how much energy was consumed by this red colored curve? In the case of red colored curve, we have spent twice more c times vdd square because we have switched on and off twice, once, twice. However, in the case of this blue signal, what happens? We seldom turn it on and seldom turn it on. So even though we have 2 times t, twice longer, however, we just took only one switching cycle. Then my question is, then how much energy is dissipated by this blue signal? Then you can immediately understand this is the case. Power consumption is just half. So now we have introduced a certain factor to describing the busyness. How busy is it? Or how active is it? So if this alpha equal to 1, it is corresponding to the clock signal. So every time period t, it is once turned on and turned off, turned on, turned off. So this in this case, our power switching or switching power consumption will be completely given by this one. But let's say that if we have alpha equal to just 0.1, then what happens? Although we have 10 clock signal, within 10, oh sorry about that, let's say that there is 10 clock signals, then our actual signal just once turn on, once turn on. Let's say that. Then what happens? In this case, its power consumption is just 10 times smaller than this blue clock signal. That is well described by this alpha, which is called as activity factor. So, however, activity factor, of course, in order to reduce your power consumption for certain logic gate, then you can reduce the activity factor. But when you have a low activity factor, then your logic doesn't work any longer actively. So usually this factor is not much changing. So this is a certain proportional number. And now this is the end of our introductory part. So now, up to now, we have spent many times for about switching power consumption on and off, on and off. And we had made an assumption that static power consumption is equal to 0. So dynamic one is quite important and static power consumption of our CMOS inverter or CMOS logic gate are close to zero. Yes, previously it was true, and dynamic power can be given by the sum of our switching power. Switching power, what is it? The one we have studied up to now, and we have also short circuit power consumption, although this is a relatively small one. And now, compared with dynamic power, in the former days, static power consumption was relatively negligible. So that's the reason why more or less the power consumption was determined by this switching power consumption. However, nowadays static power consumption is also quite much important. So it means that so let me just come back to our original discussion about CMOS inverter. Well, now we just apply a DC bias. Well, let's say the 1 volt, also say VDD, and now our capacitor is discharged, so 0 volt. And now we are trying to the static power consumption. Everybody understand in this class, understand, well, since VDD is applied, this one is on and this one is off, and we must have the serial conduction path from VDD to ground. So since it has current, so no current will flow at all. So there is nothing in this case. That was our former discussion. However, let's just come back to our homework problem also. Not homework problem, but our problem in this case. Sub-threshold slope. It means that although we reduced our gate voltage down to 0 volt, our MOSFET can have non-zero drain current. Same happens to our PMOSFET. For example, even in this case, ideally, the drain current should be 0. However, in reality, it's not 0. Then what will happen? If we have a serially connected PMOSFET and NMOSFET, and one is turned on and one is turned off, then what is the total amount of current flowing this line? This current will be determined by the current of turned off device. If PMOSFET is turned off, then the PMOSFET's leakage current will determine the current. And if MOSFET is turned off, then the leakage current of MOSFET will determine this path current. Then you know that anyhow we can have that current, then we can say that that leakage current due to what? Due to either of MOSFET and or PMOSFET multiplied by VDD will determine the power consumption of our static power. Okay, even without changing the voltage, input voltage, everything is just in its steady state, but still we have power consumption. And also, this is not, we are now talking about the current path through this MOSFET and PMOSFET. Yes, we are considering this way. However, we have also other paths. For example, here we have the common drain between MOSFET and PMOSFET, and let's say that here we have leakage current to the ground, then what will happen? Also, we have the power consumption like this. Also, here, even in the case of this source, the PMOSFET source can have certain leakage current toward this zero, then it can also contribute to the power consumption. So that's the reason why. So let me just summarize. So that's the reason why static power consumption is determined by what? Determined by leakage current. If the switching power consumption is quite much dominant over static power consumption, let's say that this is much, let's say if we have the condition like static power consumption is negligible than dynamic power consumption, then of course we are not that much care about the leakage current. However, in reality nowadays, they are more or less comparable. Then what happens? In order to reduce the total power consumption, we should be very careful about the leakage current. So now maybe you remember this one. Maybe in our previous lecture we have drawn these graphs VGS and ID, and in its logarithmic scale we have drawn something like this, and I told you that here we have a certain voltage VDD, and this current is given as I-on, and I told you that when we apply zero gate voltage but still drain voltage is VDD, this one is called as I-off. Point is I-on, that determines the maximum value of switching frequency. How fast can we charge and discharge of this given load capacitor? However, this off current determines what? Determines the power consumption. So now let's make a dream. If your dream is super fast but super power efficient system, then where should be the ions place? Should we have this place or that place? Also, in the case of power consumption, what is desirable, here or there? Everybody understand the desirable point is here and there. If we can achieve this one, then okay, we can operate our system quite fast, and the power consumption, static power consumption can be really minimized. So yes, we wanted to have much large distance between this on current and off current. And in order to reduce switching power, this is related with static power, and in order to reduce dynamic power or switching power, what should we do? The thing we can do is changing the VDD. Previously VDD was this one. However, as I told you before, if you reduce this VDD by 30%, you will get twice more efficient power efficiency system. So now you wanted to have this point. So simply speaking, let me just draw our dream. The dream is like this. If we have certain technology which can provide us this way, VGS and ID, and this one and this one compared with this one and that one. Let's say that this is our current technology, and let's say that this is our dream technology. Oh, sorry about that. Okay. Just dream technology. So what happens in this case? Since VDD is reduced, the dynamic power consumption is greatly reduced. Since off current is reduced, the static power consumption is reduced. Finally, since on current is higher, then our performance can be increased further. So now you understand my main discussion is always around these two numbers. What is these two numbers or two quantities, like speed, maximum speed of your circuit, and power consumption. So this one is typically called as performance, and power is power. So now you understand performance and power somehow in the trade-off relation. If you wanted to increase the performance, in many cases you have to sacrifice the power efficiency, or in other way, if you wanted to make a low power device, low power circuit, then anyhow you have to compromise the performance of your circuit. Okay, so that is the important message. There is nothing in free in our world, so they are in the trade-off relation. So this is the dream technology. However, my final question is, can you achieve this one? The technology which has very steep ID versus VGS curve. Why don't we just have draw our dream more drastically, like this way? Wow, but it's not possible. Why? In our MOS system, you understand 60 millivolt per decade is the limit of your subthreshold slope. So it's not possible. This kind of super steep device cannot be achieved. So we must stay relatively moderate value of subthreshold slope in this case. Okay, it was the introduction about our power consumption. So in the next lecture, we'll talk about each component. So now let's keep our discussion. And now you have time to review your midterm examination score